Hello, everyone. So last time we started the counting topic and we looked at a few things. Last time we looked at basically product rule. Product rule in the context of counting problems. So product rule said that if you want to perform few tasks, and let's say first task, let's say if you want to do two tasks, first task you can do it in n1 ways, second task you can do it in n2 ways, then in total you have n1 times n2 ways to perform that procedure. And we also looked at principle of inclusion, exclusion, which in set theory notation, we can write it as a number of elements of A1 union A2 is equal to number of elements in A1 plus number of elements in A2 minus number of elements in A1 intersection A2. Right? When you take union of two sets and you want to count the number of elements, so you have to add the number of elements in A1 and number of elements in A2. But when you do that, the number of common elements between A1 and A2 are counted twice. So if I subtract it with number of elements in A1 intersection A2, then every element will be counted once, and therefore I will get the number of elements in A1 union A2. Now this time we want to start 6.2, which is about a pigeonhole principle. So suppose that a group of 20, let's say, pigeons want to settle into 19 pigeonholes. Then, okay, what can I say then? 20 pigeons into 19 pigeonholes. So then I want to say that at least one pigeonhole will contain two pigeons, right? Because let's imagine, so first pigeonhole, let's say pigeonholes are numbered or tagged with number 1 to all the way to 19. So let's say first pigeon goes to first pigeonhole, second pigeon goes to second pigeonhole, and so on. So 19th pigeon goes to 19th pigeonhole. Then 20th pigeon must go to one of them, one of these 19, which is already full. So one pigeonhole must contain at least two pigeons. Or another scenario could be, let's say first pigeon goes to the first pigeonhole and second pigeon also goes to the first pigeonhole. Then again, already we have one pigeon with two and one pigeonhole with two pigeons. So there is no way that you can distribute 20 pigeons into 19 pigeonholes in a way that every pigeonhole has at most one pigeon. If you have 20 pigeons and 19 pigeonholes, at least one pigeonhole must contain two pigeons. There could be more. So there are other ways to distribution. For example, we can have one pigeonhole with, let's say, 5 pigeons, or let's say one pigeonhole with 10 pigeons. And then the remaining 10 pigeons could be distributed into other pigeonholes. And in that case, we have few empty pigeonholes left. So I may have even empty pigeonholes, but in any case, whether we have empty pigeonholes or not, in any case, at least one pigeonhole must contain at least two pigeons. So this is what is called the pigeonhole principle in mathematics. So let me say then, at least one. It's a little bit slow. Let me We said this. So then at least one pigeonhole will contain at least 2 pigeons. So mathematically, we can phrase this principle as follows. So pigeonhole principle so let k be a positive integer. And suppose that we have k boxes with at least k plus 1 objects, then one box, or in other words, at least one box, at least one box will contain at least 2 objects. Let's see how we can prove this. This is called principle, but although it's called principle, we can still prove it. So how can we prove it? So let me, first of all, we said we have at least k plus 1 objects. So let's call the number of objects, let's say m, for example. So let m be the number of objects. We have m bigger than equal to k plus 1, right? So we have at least k plus 1 objects. And what about boxes? We have k boxes, so first box, second box, kth box. So this is box number 1, 2, all the way to k. So I want to do proof by contradiction. So suppose that every box contains at most one element. I want to show that at least one box contains at least 2 elements. So if this is not true, then that means every box that I consider has at most 1 element, because even if one box has 2 elements, then I get what I need. So the only way that I won't get what I need is if every box, every one of these k boxes has at most 1 element, then in that case, I won't get what I need. Then, so if this is true, then the total number of objects, then the total number of objects will be at most how much? So every box has at most 1 element, and we have k boxes. So then the total number of objects will be at most k times 1, right? K because we have k boxes, and 1 because I'm assuming that every box has at most 1 element. So this 1 comes from there, and k times 1 is k. So this means m is at most k. At most k means what? Means less than equal to k. And this is contradiction with m bigger than equal to k plus 1. See, remember we had m bigger than equal to k plus 1. If m is bigger than equal to k plus 1, of course, it's impossible that m is less than equal to k. All right, so let's look at an example. Suppose that we have a group of 366 people, then at least 2 people share the same birthday. So then show that. And also please ignore the leap years. So ignore the leap years, assume that every year has 365 days. And if you have 366 people, then at least 2 people share the same birthday. How can I prove this? Well, intuitively, this is almost obvious because, you know, the only way, if I want to try to have distinct birthdays for these people, well, let's say first person has some birthday. Second person is not allowed to have that birthday anymore if I want to have distinct birthday. So second person will have his or her birthday on the second day, and third person on the third day, all the way to 365th people on the 365th day. And then all days are already full, right? Meaning that I have put the name of one person with that birthday. So 366 people must, his or her name must be put on one of these 365 days, which are already full. And therefore, at least one day will have the name of 2 people on it. But so this is one way to justify it. But the easier way is to use the theorem that we just proved, pigeonhole principle, right? Because we already mentioned the reasoning once when we wanted to prove the theorem. So we don't have to repeat mentioning the reasoning every time. I mentioned the reasoning one time to prove the theorem. Now that I've proved the theorem, I can just use the theorem. I don't need to prove it every single time that I want to solve a problem using it. So how can I use this one? So if I want to use pigeonhole principle, I need to have a positive integer k and k boxes and at least k plus 1 objects. So what are the boxes here when we have people and birthdays? So the days here will be the boxes. So every year, because we remember we ignore the leap years, so every year contains 365 days, which can be considered as our boxes. See, we have so January 1, January 2, December 31. Now I have 366 people. So here, k equals 365. We have k plus 1 equals 366 people. So instead of objects, we have people, and that's okay. The concept is still the same. Then at least one box will contain two objects, or in this case, two people, or the name of two people. So by pigeonhole principle, at least one day will contain the name of, let me say, will contain the name of at least two people. And that means at least two people will share the same birthday. So let me give you a similar exercise here. What about months? How many people do I need in order to be sure that at least two of them share the same birth month instead of birthday, birth month? So let's say, for example, two people, at least two people whose birthdays are both June, for example, or both January, for example. So two people with the same birth month. How many people do you think I need at least? So suppose that we have at least 13 people, right? This time the boxes are months, so January, February, all the way to December. Right? So we have 12 boxes. Now, if I have 13 people, then I can say that at least one box or at least 1 month will contain the name of at least two people. So suppose that we have at least 13 people. Show that at least two of them share the same birth month. Okay, so the next question I want to ask here is at least how many people do we need to have in order to guarantee the existence of at least 3 people with the same birthday? Three people with the same. So pigeonhole principle helped us to find the minimum number of people for having at least 2 people with the same birthday, and the answer is 13. If you have at least 13 people, then at least 2 of them will share the same birth as a birth month, and 3 people with the same birth month. So how many do you think we need? Well, let's again consider the, let's say, worst case scenario. If I want to distribute people into months, to avoid repeated months, basically. So let's say if I have 12 people, I can have 12 people with all different birth months because I have 12 months. It's possible. Of course, it's possible to have, even if I have 12 people, of course, it's possible to have 2 people, or even 3 people with the same birth month. That's possible, but it's not about being possible. The question is about having a guarantee to have at least 2 people or at least 3 people with the same birth month. So it's very important, this word, that we need to have a guarantee. It's about having guarantee. It's not about being possible, right? So even if I have only 3 people, it's possible that they have same birth month, but it's possible that they don't have same birth month. So how many do I need in order to have a guarantee? If I have 12 people, I still can have 12 people with all different birth month is possible. So I cannot have a guarantee that even 2 of them have the same birth month. But once I have 13 people, because I can distribute 12 people into 12 months, all having different birth months, but then 13 people must be put into one of the months that is already used and has a name of a person in it. So then if I have 13 people, I will have at least 2 people with the same birth month. Now, again, let's say if I want to try to avoid having 3 people with the same birth month, what can I do? So 13th person can go to one of the months, then 14th person can go to another month other than the one that I put the 13th person. So with 14 people, again, I can I can distribute them in a way that at most 2 people have same birth month, not 3 people. But again, 15 people, same thing, 20, all the way until 26. Even if I have 26 people, I can still distribute them in a way that, say 24 people, if I have 24 people, still I can distribute them in a way that every month contains 2 of the people, right? So January, I put 2 people. February, I put 2 people. All the way December, I did 2 people. So even with 24 people, it is still possible that every month has at least 2 people having their birthdays in it. But once I have 25th person, because already every month has been used with 2 people, once I have 25th person, then I can say that 25th person must be put, his or her name must be put in one of the months, and every month already has 2 names in it. So then once I put the name of 25th person on that month, then I will have at least 1 month with 3 people in it. So the answer, in order to have guarantee, in order to have 3 people of the same birth month, is 25. So how can I generalize this as a rule? So basically, because I had 12 months, right? So 24 over 12 still is 2. And so it was not acceptable. But 25 over 2 is 2 point something, right? And then if I take ceiling of that number, because 3 is the ceiling of 2 point something, right? So if I take the ceiling of that number, then I get the minimum number of objects in one box, basically, if I want to talk in the language of objects and boxes. If I have 25 people with 12 boxes, or in this case, months, then the guarantee that I can have is to have at least the ceiling of 25 over 12, the ceiling of number of objects divided by number of boxes. In that case, it's going to be 25 over 12, and the ceiling will be 3. I can have a guarantee that at least one box will contain at least the ceiling of number of objects over number of boxes. So this is called the generalized pigeonhole principle. So it will say here that to answer this question, we need the generalized pigeonhole principle, which can be phrased as follows. So generalized pigeonhole principle. Suppose that, again, let's say n and k are positive integers. If we have k boxes with n objects, then at least one box will contain at least ceiling of n over k objects. Let's see how we can prove this. Proof, and proof by contradiction. See, we have k boxes, box number 1, box number 2, all the way to box number k. Suppose that each of these boxes and contain at most ceiling n over k minus 1 objects. So again, let's think about it. I want to say that at least one of these boxes has at least ceiling n over k objects. So ceiling n over k, let's call it L, for example. It's just a number, right? I want to show that at least one of these boxes has at least L objects. If this is not true, what does that mean? That means every one of these boxes will contain at most L minus 1 objects, because if even one of them has more than L minus 1 objects, means that box will have at least L objects, which is exactly what I need to show. So if what I want in proof by contradiction, we assume what we want to show is wrong, right? So if what I want to show is wrong, meaning that it's not true that at least one box will contain at least L objects, that means every one of these boxes must contain at most L minus 1 objects. And what is L here? The value of L is ceiling n over k. And where is this ceiling n over k coming from? I try to basically justify or motivate, basically. I didn't prove anything, but I just try to motivate that where this number ceiling n over k is coming from, because, you know, in the case that we had 3 people, we want to have at least 3 people. In the case of having 12 boxes, then we need 25 objects, which is ceiling of 25 over 12. So we could get the idea or make a guess basically from that example that the number here must be ceiling n over k So suppose that each of these boxes will contain at most this many objects, then the total number of objects, will be at most, how much? See, each of these K boxes contains at most this number L minus 1. I called it L minus 1 or ceiling N over K minus 1 objects. Each of them. So at most, how many objects will I have? I will have K times ceiling N over K minus 1, right? Each box contains this many, at most this many elements, and there are K boxes in total. So in total, I'll have K times this, at most K times this many objects, which is going to be less than or equal to. Now, what can I say about ceiling X? I said just less than, so not less than. So ceiling X, I can say is always less than X plus 1. Check. We can prove this using definition of ceiling of a number, which we did in the previous chapters. But again, if I want to give you the idea why this is true, ceiling means the smallest integer greater than or equal to the number. So if the number is integer itself, like 5 or 6, for example, if the number is 5, the ceiling will be also 5. And of course, 5 is less than 5 plus 1. So in that case, there's no problem. If the number has some decimals, let's say 5.1, then the ceiling will be 6. And 6, which is the ceiling, is less than 5.1 plus 1, which is 6.1, right? So whether the number has decimals or no, this will be true. I just gave you some examples. Of course, you know that the examples are not proofs. You can prove it using the definition of ceiling. But I just wanted to give you the idea that why this is true, that the ceiling of a number, any real number, is always less than X plus 1 for every real number X. For every X. So I can say that this is less than, now my X here is N over K. So I can say this is less than K times N over K plus 1 minus 1. And this is N. So I showed that we showed that total number of objects is less than K, less than N, right? And this is contradiction. So this guy here is the total number of objects. The total number of objects is at most this number. And this number is already less than N. So total number of objects is at most some number which itself is less than N. So that means total number of objects is less than N. And this is contradiction with total number of objects being N. Okay. So now let's look at example above. So we finished the proof. In example above, let N be the minimum number of people that we need in order to have at least 3 people with the same birth month. So here, how many boxes do we have? Here we have k equals 12 months. And n people. So by pigeonhole, generalized pigeonhole principle, we have at least n over k ceiling, because k is 12 people with the same birth month. And I want this number to be at least 3. So the minimum n value for which this number here, ceiling n over 12, is bigger than or equal to 3 is, so what n value do I need in order to have this ceiling to be at least 3? Well, we can do it by inspection. By inspection, if n is 24, 24 over 12 is 2, and ceiling of 2 is 2, which is not bigger than or equal to 3. But once we exceed 24, meaning that if we get to 25, then 25 over 12, the ceiling is bigger than or equal to 3. So the minimum n value for which this is bigger than or equal to 3 is n equals 25. And note that for n equals 24, we can have every month with the name of exactly 2 people on it. So we really need at least 25 people, because for 25 people by pigeonhole principle, we will have at least 3 people with the same month. And this 25 is really the minimum number, because if you go one less, which is 24, then we can distribute them in a way that every month contains 2 people in the name of 2 people. So we cannot have a guarantee to have at least 1 month with 3 people, with 24 people, right? In order to have a guarantee, 24 is not enough. We can't have guarantee, but 25, we have a guarantee by generalized pigeonhole principle. So the minimum number of people required to have 3 people with the same birth month. Same birth month is n equals 25. Okay. Here the next example. How many cards? How many cards must be selected from a standard deck of 52 cards to guarantee that at least 3 cards of the same suit are selected. So this is part A, and part B. How many must be selected? From a standard deck of 52 cards. Standard deck of 52 cards. To guarantee that at least 3 hearts and at least 3 hearts are selected. So let me remind you about the 52 card standard 52 card deck. So we have 4 suits. The 52 standard, let me say recall. So you probably have seen this in your other courses, for example, probability theory, about a standard deck of 52 cards. Standard 52 card deck. So we have 4 suits. 2, 3, and 4. And then we have 4 suits. So the suits are hearts and clubs and diamonds and spades. And each of them has 13 ranks. So it's going to be ace, and then 2, 3, 4, 5, and then 10. And then, okay, see, I don't have enough space here. Let me see. We have ace, 2, 3 to 10, and then we have jackward and queen and king. So ace, 2, 3 all the way to 10, and then jackward, queen, king. So these are in the order of the ranks. So in some games, ace is counted as 1, but some of them is the highest one. Most games is the highest one, so even higher than king. So you could put ace after king, or sometimes it's counted as 1, so you could put it before 2. So that depends on the game. But these are the ranks. So again, same thing for all suits, it's the same ranks. So hearts, we have ace, 2, 3 all the way to king. Again, clubs, we have ace, 2, 3, 10, jackward, queen, king. Again, same thing here. And same thing here. Okay, so we want to know how many do we need, at least how many do we need in order to have a guarantee that at least 3 of them have the same suit. So here again, if you want to use pigeonhole principle or generalized pigeonhole principle, you have to think about boxes versus objects. What are the boxes here? The boxes here are the suits, because I want to have at least 1 suit with at least, for example, 3 objects here. So in pigeonhole principle or generalized pigeonhole principle, we have at least 1 box with at least certain number of objects. So here boxes are suits. So here, part A, we have a K equals 4 boxes or suits in order to have guarantee that we have at least one box with 3 objects, or here objects are cards, by pigeonhole, generalized pigeonhole principle. Because pigeonhole principle is about at least one box having at least 2 objects. If you want at least 3 objects or at least 4 objects and so on, you need to use generalized pigeonhole principle. We need to have, in order to have a guarantee that you have at least budget, we need ceiling of n over k to be bigger than equal to 3, and k here is 4. Ceiling of n over 4 bigger than equal to 3. So that will happen if n is how much? So for 8 over 4 is 2. The ceiling is not bigger than equal to 3, but 1 bigger than 8, 9. 9 over 4, the ceiling will be 2 point, will be ceiling of 2 point something, which is 3. So the mean number, mean n satisfying above inequality is n equals 9. Ceiling of 9 over 4 is bigger than equal to 3. Note, with n equals 8, we can have every suit, or it is possible to have every suit with 2 cards. So for the n equals 8, I cannot have a guarantee that at least 3 cards will have the same suit, because it's possible that every suit has 2 cards, or the name of 2 cards on it. Okay, so we cannot have such guarantee, but for n equals 9, we can have a guarantee for at least 3 cards having at least 3 cards having the same suit, or in other words, at least 1 suit having the name of at least 3 cards on it by generalized principle and pigeonhole principle. So the minimum number n that we're looking for is n equals 9. So mean number of cards required is n equals 9. Okay, so this is for part A. Okay, what is the difference of part B now with part A? Part B is asking about having at least 3 cards being hearts. Part A was saying that at least 3 cards having same suit. So same suit could be anything. Could be, we could have 3 cards with all of them, with all 3 of them being hearts, or all 3 of them being clubs, and so on. Any of those cases would be acceptable. But in part B, we're requiring having 3 hearts, 3 cards being all hearts. So what is the difference? For example, if I have 3 cards which are all clubs, 3 cards or 3 clubs, if I have 3 clubs, is acceptable in part A, but is not acceptable in part B, because in part B, I am only asking for having 3 hearts. So 3 clubs is not acceptable, or 3 spades is not acceptable, and so on. So how can I guarantee of having at least three hearts? Well, if I want to use pigeonhole principle or generalized pigeonhole principle, let's look at the statement one more time. Generalized pigeonhole principle talks about having guarantee for having at least one box with at least certain number of objects. You know, pigeonhole principle itself also talks about having guarantee for having at least one box with at least two objects. So it talks about having guarantee of having at least one box. It does not specify which box. Remember, we have K boxes. It tells us that at least one of those K boxes have certain number of objects. But it doesn't say which box. It doesn't say box number 1 has at least a certain number of objects, or it doesn't say box number 2 has certain number of objects. It just says at least one of those K boxes. But what we need here, so let's say if I call, for example, heart box number 1, club box number 2, diamond box number 3, spade box number 4. In part B, we want box number 1. We want box number 1 to have at least 3 objects or 3 cards. So not any boxes, just box number 1. I want to have at least 3 cards there. So how can I do that? So I cannot use pigeonhole principle or generalized pigeonhole principle because both of them guarantee that at least one box having certain number of objects, they do not specify which box. But here I want to specify which box. I want to say that box number 1 must have at least 3 objects. So first of all, the very first thing I want you to notice is that we cannot use pigeonhole principle or generalized pigeonhole principle. So note that we cannot apply pigeonhole principle or its generalization since they do not guarantee a specific box having certain number of objects. Instead, so we cannot apply a pigeonhole principle or generalized pigeonhole principle. Instead, what should we do? Instead, we must think of the worst case scenario because I want to have guarantee, right? So it's not about being possible. Of course, if I have only 3 cards, it's possible that all 3 of them are hearts, which is what I need here. I need to have at least 3 hearts here. So it's not about what is possible. It's about having guarantee. So when can I have a guarantee for having at least 3 cards? So I have to think about the worst case. So for example, if I have 12 cards, it's possible that all 12 of them are clubs, for example, and none of them are hearts. Even if I have 24 cards, it's possible that 12 of them clubs, 12 of them spades. Even if I have 36 cards, it's possible that 12 of them clubs, 12 of them spades, 12 of them diamonds, and still it's possible that I have no hearts at all. But if I have more than 36, so 37th card, if I have 37 card, then I have at least 1 heart, because even if the worst case scenario, I have already withdrawn all other cards. I have no cards left other than hearts in the worst case scenario. And 37th card must be heart. So if I have 37 card, I will have at least one heart. Similarly, 38th card, I will have at least two hearts because remember in the worst case scenario, everything else is gone. And if I have 39 cards, I will have sorry, I have 13 from each suit, not 12. I was thinking about 12. I have 13 from each suit. So if I have 13 cards, I can have all in one suit, 26 cards all in two suits, 39 cards, I can have all in three suits. 40th card, if I have 40 cards, then I will have at least one heart. 41 cards, I will have at least two hearts, and 42 cards, I will have at least three hearts. Right? So in worst case scenario, if we have 39 cards, we still may not have any hearts. Right? Remember, it's about having guarantee, not about something being possible. Of course, if I have 39 cards, it's possible that I have 10 hearts, but I cannot have a guarantee because in the worst case scenario, I can have 13 clubs, 13 spades, 13 diamonds. Wait, let me write with 13 clubs, 13 hearts, 13 diamonds. So 39, I can have no hearts at all. Now, if we have 40 cards, then we must have at least one heart, because all 39, if I want to avoid having hearts, because I want to have a guarantee, therefore I have to think about the worst case scenario. So if I want to avoid hearts, I can avoid it by until 39 cards, but 40th card, then all other cards are gone. So 40th card must be heart. So even in the worst case scenario, if I have 40 cards, I will have at least one heart. If we have let me write since even in the worst case scenario, all other cards are gone. By 39th card, and 40th card must be hearts. Similarly, if we have 41 cards, then we will have at least two hearts. Because again, 39 cards, all other cards are gone. In the worst case scenario, 40th and 41st card must be both hearts. So we'll have at least two hearts. And again, similarly, Similarly, if we have 42 cards, then we will have a guarantee to have at least 3 hearts. Note that n equals 42 is the minimum n value to have such guarantee, because because in the exam, let's say if you're claiming that n equals 42 is the minimum number that for which you have a guarantee, there are two things you have to show. You have to show that for n equals 42, you have a guarantee, and also show that this is the minimum number that you have a guarantee, meaning that if you have one number less than that, which is 41 in this case, you will not have a guarantee for one number less than that. And then these two together will mean that 42 is the minimum number that we can have a guarantee. So mean n value to have such guarantee for n equals 41, we won't have a guarantee to have at least 3 cards, 3 hearts, because since it is possible to have 13 clubs, 13 diamonds, 13 spades, and 2 hearts. So mean n required to have at least guarantee for having at least 3 hearts is n equals 42. Okay, so this was an example, part B. Part A, we use generalized pigeonhole principle. Part B, it was a similar example with a similar concept, but instead of having at least 3 same suits, we had at least 3 hearts, specific box. Therefore, we could not use pigeonhole principle or generalized pigeonhole principle. Instead, we used a similar idea. So the idea was similar, but it was not pigeonhole principle or general pigeonhole principle, because we were looking to have a specific box having at least certain number of objects.